Okay, hello, and welcome to Lit Reviews Day Tuesdays. I am absolutely an hour and a half late, but Review Tuesday will plow on despite this, and despite the fact that I have to leave a little early because I have an appointment. We're struggling here on the channel. We're struggling with timing. We're struggling. I set a schedule. Apparently, I can't stick to it very well, but we struggled. That's how you do it. You try, you figure it out. Are we going to modify that schedule? Yeah. Yeah. Let's modify the schedule. Not today. Mm-mm. Sometimes I'm early. Sometimes I'm late. Why is that? This morning I had to go do cuddles with my lover. You can't predict that in a schedule, you know? And when you need cuddles, right? Someone needs cuddles. We're going to look at some reviews day. We're going to look at some literature, top literature on Google Scholar today. I like using the top articles from Google Scholar. It always gives us a really big peek at what the big stuff was. Very satisfying. Oh man, I've been playing so much Satisfactory lately. It's getting unreal. I should just be playing it on stream, I know, but it's very unstructured and very creative. And I step away from the keyboard a lot when I play. You know, when I play video games, there's like a lot of walking around and thinking and ruminating in between the steps that I take in the game. So there's a deliberate and slow process. I missed Factorio Friday last Friday. Again, I had an appointment, so it was something at work and it came up last minute, but I said I would be there in person to speak with those departments, and I did. So I just wish I hadn't had to sacrifice a stream for it. And I won't do that again. Seriously. The meeting has to be way better than that for me to cancel a day. Just saying. So let's see here. What do we got? Let's do a little screen share, shall we? A little screen share. Here I am. Yeah, I love this. Is this somehow different? I always wonder. For literature review, I feel like right-hand side. There's a lot of columns, you know? There's a lot of columns on the right-hand side of our articles that we can just chop off up here. Advertisement space. To strategically cover advertisements. All right, let's go Scholar here. We could let's pick a subset here for the category just to give it some kind of coherence. Um, and honestly, I owe it to myself and to other people to just check into physics and math and see what top articles are getting cited and if those top number of citations are significant or not. Health and medical science, always interesting. Could be picking engineering and computer science, but we know what's in that category. We had MOSFET developments. We know that NumPy got a huge Nature article in 2020, 2022. That was so weird. Honestly, I keep having recurring thoughts about that. I'm like, it's great that we have. It's this paper right here. It's the it was in the IEEE paper, Conference on Computer Vision and Pattern Recognition. And they're like NumPy deserves a tip of the hat at any moment. NumPy, the whole Python stack that got us to machine learning, all of that deserves a lot of acknowledgement. But were they scientific discoveries, or, you know, are they as site-worthy as the creation of NumPy in the first place? I wouldn't say so. I thought NumPy has a lot of internal novel solutions, and it lacked a significant publication for many years. So in many ways, it's like an overdue publication, but I've been using NumPy for so long, it just doesn't sit right with me. to be giving it a fresh article. What happened to my captions? Are they too little? I spoke too much. I noticed that it was just canceling off all the captions. What? So, physics and math? Is that what we're doing here? Physics and math? Phys review letters? Phys review letters, excellent. Astrophysical journal, this is going to be way out of my wheelhouse, and it's nice to be branching out. Phys review D, excellent. Let's just ask ChatGPT about which opinions it has on these top 10. Let's take the top 10, actually. Yeah, I got it, Windows. We use the tools. I don't know if I can actually save this in my... Can I just save it to the desktop? Top 10 Phys Math. Google Scholar. Journals. Let's just let chat have a look. Brief bullet points for each journal on the common knowledge of the journal. That surrounds the journal, really. Oh, Phys Review is the flagship journal of the American Physical Society, I see. I remember that they're short, yeah, high-impact papers. This is going to be a great place to dig in, Phys Review letters. The APJ. Again, I'm not well-versed in observational or instrumental research in astrophysics, so probably Astrophysical Journal APJ is not going to be a big part of what we look at. And I'll be glad to be poking into Phys Review letters, I know that. Highly selective, focuses on the results of the fundamental significance. Yeah, that's my bias. That's my bias. That's why I think publications and journals in general should be focusing on the results and the fundamental significance. Which again, the IEEE publishing a NumPy paper, although NumPy certainly deserves the acknowledgement, so late in NumPy's existence doesn't feel like a result, first of all. It's not a result, it's a tool. And it's not of fundamental significance because it's been around for 15 plus years. I'm going to bitch about that all the time. I don't know if I'm ever going to let go of that problem. Why did NumPy get a huge publication? And I love NumPy. I am the NumPy advocate. It's not just that I don't even have anything against it. I have myself personally shepherded dozens of people into the programming language and into the library. Physicists and students alike. And I'm proud to have done that, yeah. I think NumPy is amazing, certainly deserving of acknowledgement. Okay, let's keep going. Phys Review D, PRD. PERD. Somehow PRD seems like so much less sophisticated than Physical Review D. Specialized for particle physics, field theory, gravitation, and cosmology. See, this is why I'm embedded into Phys Review D, is because most of the relevant literature for a particle physicist is there. It's the go-to venue for theoretical high-energy physics, although I'm not really diving into theoretical physics, but that is exactly why we conduct the experiments we do. Frequently publishes long mathematically dense research articles. The IEEE Transactions on Geoscience and Remote Sensing, the TGRS. Tigers. Go Tigers! Focus on satellite observations, image processing, and geoscience instrumentation. What's this? Important notifications? Sure. Also, the transactions on geoscience and remote sensing is known for methodological and algorithmic innovation. Monthly notices of the Royal Astronomy Society. Oh, yeah. Okay. Okay. A lot of astronomy here. A lot of astronomy journals here in the top 10, right? Like what we were looking at the subcategory, the category, physics and math. Yeah, that's right. Top publications by category, physics and math. And we just took the top 10. Like we didn't subcategory this. We do physics, I guess. But I just wanted to see as a whole, who's getting the publications? Where's the H index? Who's reviewing? And in some part, the number of citations and the H index, therefore, it's just tied to the number of people in the community, right? The more people that there are writing papers inside of a community, the more number of citations there will be in that community, since the people in the community are writing and making those citations. So it would be very significant to be found near, not at the top necessarily where the most outstanding articles are reviewed, but it would be significant to be in and amongst near the top of this list, knowing how niche these communities are. I mean, let's just, for example, chaos, solitons, and fractals. How many people on Earth are working on chaos, solitons, and fractals to the point where there's a whole journal dedicated? Certainly there should be. Certainly there needs to be a place in a journal. But then to see that there's an H index of 129 on chaos, solitons, and fractals, right? And look, right away, here's your answers. Why are there so many citations coming out of these weird mathematical modeling components? Well, because there was a big COVID paper, an analysis and forecast of COVID-19 spreading in China, Italy, and France. And they used models that fell clearly into the chaos, solitons, and fractals paper. I bet they were thrilled. I bet the publishers were thrilled to have it here. Time series forecasting of COVID-19 transmission in Canada using LSTM networks. Applications of machine learning and artificial intelligence for COVID-19 pandemic. An SIR model assumption for the spread of COVID-19. The top papers, all the way, like 1, 2, 3, 4, 5, 6. The top 6 papers in this journal. That is the highest cited papers by a margin as well, reaching 1,250 there. All those top papers in this journal, COVID papers. COVID papers. News article picks up COVID paper, gets a ton more citations and views, right? I don't know. It's a niche. It's a niche inside this community. So I'm not even saying that's weird. That's an artifact. Is that the same for science and applications in light? No, these are actual scientific developments. Mini LED, micro LED, OLED displays, augmented reality and virtual reality displays, emerging technologies. Well, a lot of aggregate studies. Do you see that? These 2 studies at the top are really pulling the weight of the bottom way up. That's what defines your H index. You get cut off here where the number of citations passes the number of articles below a place where N is less than the citation index. God, definition of H index here. But it's so artificial. It's like this paper has a high H index because it was, there's a significant number of publications at the top here. So what are we seeing? We're seeing actual physical implementations of electronics. We're seeing thermal conversations. We're seeing electromagnetic conversations. We're seeing phase imaging with an untrained neural network. We're seeing low-dose real-time X-ray imaging. We're seeing scintillators. Again, it's going to be a lot of photonics. It's going to be a lot of, yes, lights up. Photonic matrix multiplication lights up photonic accelerator and beyond. What? What? Sure, I accept every cookie. I am a cookie monster. Nom, 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 nom. Give me those cookies. I don't just accept them, I inhale them all. The photonic matrix multiplication lights up photonic accelerator and beyond. Okay, matrix computation is fundamental, sure. Yeah, we know this. Photonic accelerators are designed to accelerate specific categories of computing in the optical domain, especially matrix multiplication. Oh, I see. Photonic matrix multiplication. Oh my God, for super fast light-based instead of instead of potential-based calculations like we do over a wire, go over optics. This is a great idea. This is amazing. Who published this? Zhao and Dong? What's the institution? The Wuhan National Library Laboratory for Optoelectronics. Again, the National Laboratory for Optoelectronics. And again, yeah, excellent. Yeah, wow. What's the outcome? They summarize the development milestones of photonic matrix multiplication and related applications. Then we review their detailed advances in applications. Finally, we comment on the challenges and perspectives of photonic matrix. So they didn't actually accomplish it, right? People are dying for this. Like when I hear about light-based calculation, I know it's the future. I know that's because light is so much faster than the electrons that we use right now on our copper circuits. So a photon-based calculator of any type, needless to say, a matrix calculator is the best because it can calculate neural networks. But like, no matter what it is, if you're calculating it in light, that's the sweet spot. You want pure light as well. And this came out of Nature. They ended up publishing in Nature later. It is a review article, right? These are larger perspectives on where photonics is at. This is huge, yeah, but people are so thirsty. I feel like this was a bait article. There's like 56,000 accesses on the article and 460 citations. Holy cannoli. Ultra-fast and broadband photodetectors. Oh yeah, we love this. We love the idea of detecting and security. We love security in the broader literature community, I think. People love to do it faster. How fast can you both capture the image of a human doing something and process it by a neural network? We're all asking that question all the time. How fast can we do this? How fast? High performance quasi 2D perovskite light emitting diodes from materials to devices. Who are we talking about here? This is another review article published in 2021 where it tells us that perovskites, can I please get some pronunciation on what this is? Love it. Let's get some volume as well. Can we simply hear this?
Next generation of solar panels are here. A tandem perovskite solar panel with higher efficiency than silicon alone has just arrived on the market. And the first batch has already been purchased by an undisclosed US customer, which will soon install them into a 15 to 20 megawatt plant alongside traditional solar panels. Now this isn't just hype, this is happening. And to be clear, this video is not a plug or a sales pitch, but perovskites, whether used in hybrid setups or as fully functional solar cells, have finally materialized.
Wait, so perovskites are a competing but also supporting technology of solar cells?
Thanks to some big breakthroughs at Oxford PV. And that's not the only research team that's propelling perovskites into the present. So how did Oxford PV pull it off? What's the catch? And has anyone else cracked?
Oh my God, what's the catch? Please, please, please help. We're literally spending so much effort to see these science videos.
The code on perovskite durability issues. I'm Matt Farrell. Welcome to Undecided. This video is brought to you by Surfshark. General. So why is this such a big deal? Well, let's quickly recap what perovskites are and how they've finally broken out of the lab and into the market. And
I totally missed this development. And developments, again, fundamental material developments are absolutely the game changers in the technology landscape that
In
we
simple terms,
see.
perovskite describes any material with the same crystal structure as calcium titanium oxide. As we've talked about on the channel before, crystalline structures are incredible at efficiently moving electrons. I spoke with Oxford PV's Chief Technology Officer, Chris Case, who explained why this crystal structure is so important.
I always like to remind people, salt and diamond have the same crystal structure, but boy, are they different materials, right?
Oh boy, have you ever tried to put diamonds on your food? Yum.
Just as, graphite and diamond have different.
This is like our best scientists as well. Like they didn't go to comedy school. They didn't take any acting lessons. No one got them camera ready. I'm sure this was filmed on somebody's personal laptop, right? That doesn't in any way discredit the information. Curiously, it even adds to the quality or to the trust I have.
For things, but they have the same material. So the orientation of those atoms is quite unique. In the case of the perovskite for solar, there are different atoms that were combined, yet they uniquely do something that makes them very good as a solar absorber.
Perovskite solar cells could be a game changer compared to silicon, which is the current go-to material for PVs. Silicon is durable, affordable, and relatively efficient, but is bumping up against a theoretical efficiency limit of about 33.7%, known as the Shockley-Quasar limit, named after the two physicists who discovered it.
I see. So there's a theoretical limit on silicon's absorptive power here.
Enter tandem cells, which stack silicon and perovskites to push past that limit. Perovskites start in the high 20% range for efficiency, which is higher than standard silicon panels that are available today, and are theoretically capable of much, much more, and the implications are huge. But there's a catch. While perovskites outperform silicon in almost every key category, there's one glaring weakness: durability. Historically, they've degraded quickly because they don't get along with oxygen, moisture, heat, or UV rays, which is not ideal for something designed to soak up sunlight outdoors. So how has Oxford PV engineered a tandem perovskite solar panel that can last 25 years?
Yeah, wow. That's not subtle. When you leave something outside for 25 years, what are we talking about? It's like, it's got to be a building, or it's got to be engineered in a way that pushes water off of that structure and somehow deflects radiation. Like there's so many levels of having to be proof in the out of doors.
That info is still largely proprietary, which, let's be honest,
that info is, quote, largely proprietary. They got to publish on this, though. Look at the look on his face as well. What a smarmy son of a gun.
shouldn't be surprising and kind of makes sense.
Yeah.
If Oxford PV's perovskite...
Yeah, no, for human success or whatever, we're not going to share the results. I know, that's how humans do best, I guess.
solar cells last the claimed 25 years, they're sitting on a gold mine. Or should I say sun mine? Anyway, it's no surprise that they're not eager to share their secret formula. But don't worry, the cell's performance have been independently verified by Germany's Fraunhofer Institute, a trusted name in PV research. Case also gave me the broad strokes of Oxford PV's team's approach to tackling perovskite durability.
So our goal has been to reduce the degradation or sort of improve the...
Look at this guy's fun tie. This is a Van Gogh tie, isn't it? The Starry, Starry Night tie?
Performance and reliability of the device. So the combined device meets that same kind of 25-year performance expectation. And we've spent certainly the bulk of our R&D on perfecting and improving reliability and reducing degradation. And the approach was not mysterious because we found that some of our devices 8 years ago lasted tens of thousands of hours under high stress conditions.
Oh, interesting. They bumped into reliability in their laboratory and then they started looking into it.
But not all of the devices. So that told us something important. When you have a complicated problem, which is multi-components, multi-chemicals, and multiple layers of materials and things from the raw chemicals all the way through the device and all the way to the packaged device, it's a lot of stuff ripe for machine learning approaches. So we identified the key sort of degradation and defects at each of the places, just the key ones, so we can come up with a product that's good enough for the market. And that's what we've done. So we do have things that we do to control stuff at the interfaces and to passivate those grain boundaries, and of course to make the package very effectively sealed against the environment.
Now again,
Boy, that's written like a marketing pitch, not like a scientific article confirmed. And this is amazing. This is an absolute gold mine in terms of the buy-in, the number of governments or the number of individuals or corporations that are interested in securing energy independence will continue to grow as the resources that we have access to, the energy generating resources like oil, as they become limited. This is huge.
And to be clear, Oxford PV isn't
okay. So perovskites, they're just slapping crystals on top, and they're getting more output.
Pure perovskite cells. It's shipping perovskite tandem cells. If you're going to beat the Shockley-Quasar limit, like I mentioned a while
and you have to slap the perovskites on top of an existing solar cell
ago, why settle for one material when you can combine two?
Yeah.
Tandem cells are exactly what they sound like. Two types of cells working together in tandem. It's kind of like a buddy cop movie of the solar world.
Do you understand the words that are...
Oh my God, no. And we will never reference these movies is my guess, even if they're fantastic.
coming out of my mouth?
Silicon is the grizzled vet who's too old for this stuff, while perovskite is the hotshot, smart-ass rookie, who also happens to be a lot more fragile. In Oxford PV's case, that means a trusty silicon base topped with a perovskite film, all sealed up to protect it against the elements. But there's more to it than that. But before getting to that though, I need to talk to you about...
Yeah, there's way more to it. We already talked about how the perovskite cells break and crumble under radiation and other conditions. So there's so much more to it. That's really helpful. Appreciate that. Perovskites, these are quasi two-dimensional perovskites that we're talking about, which have attracted extraordinary attention. The article goes on to self-gloat. This is a review article, this is not a publication from that group of the UK, right? Because that group can't publish their results without revealing the methods, right? It's too bad. Let's just look for perovskites there, maybe. Nothing. Perovskites? Did I not spell that correctly? Perovskite. Maybe just perovskite. Nope. Okay, that's a little unusual because I do see the word perovskite here. Am I not spelling that correctly? Perovskite. S-K-I-T-E. Perovskite. Not sure what the search even does on this page. So what else do we have here? We've looked a bit into light and science applications. We know great things are happening here. So anytime I'm offered the opportunity to pop into, what was it, light science and applications, I'll always take a look at that. That was awesome. Who else really stands out? Let's just take a look at Phys Review letters. I said I would. Let's just take a quick look. Measurement of the positive muon anomalous magnetic moment. Let's go. Okay, so we are just nailing down the properties of the particles in the particle model. Is there some background around why this is kind of a challenging measurement, or why specifically we made that measurement? Let's see, who published this? It's Abi and Albari. Can I get a, let's see, show more. 44, collaborating institution, well, a lot of collaborating institutions. Around Michigan, an Italian group is here. Illinois. Who else is here? The Republic of Korea and Russia. Another Italian group. Brookhaven is working on it. Washington State. Yeah, wow, a lot of... Oh, deceased. Oh my goodness, there's people on this list who are dead. Goodness. Certainly, that happens all the time too. And because I still have some of my classic email addresses from my time working in laboratories like CERN, I get emails weekly about the death of very significant scientists whose name no one knows, right? Like this guy who dies, that We should just go through my email and look through that list. It's definitely obituaries that are worth mentioning. But they'll go on to talk about the working group that Hans was in and all of the very significant contributions that Hans had made. And it's really just so wonderful to acknowledge and to recognize how significant the number of people are who are working together in these scientific collaborations. I know it's sad to get an email about someone's death, but I didn't know that person personally. Like, it's not skin off my back. And it just reminds me that our lives are finite. The things we do, they matter. They can matter. They tangibly impact the future. When we make the decision to step up and do, and to be consistent, or to learn, or to listen, who knows where fucking around and finding out will lead us. Okay, so let's see here. These are the first results from Fermilab of the muon G2 experiment for the positive muon magnetic anomaly. The positive muon magnetic anomaly. Can I just get a quick description of what that is? Oh, let's put this in your chat. Yep. What is the positive muon anomaly? It refers to the small difference between the muon's actual magnetic moment and the value predicted by assuming it is a simple point-like particle. Formerly, it was defined as, oh, I see. So the muon isn't point-like. For a point-like spin 1/2 particle, the G factor should be exactly 2. But quantum effects, interactions with the virtual particles in the vacuum, oh my gosh. So nonsense like the Casimir effect, and literally it's the vacuum background, the quantum reality we live in, the so-called fabric of the rig that makes up the universe. It slightly differs from 2. That's its corrective effects. Amazing. Feels like a simulation all the time you look around. It's like, should be exactly this, and then there's a bunch of light-based calculations. This deviation is what we call the muon magnetic anomaly. I mean, calling it anomalies is a little misleading. These are the observations. These aren't anomalies. That's the truth. And the positive part of the positive muon anomaly comes from the positive muon charge state. So does the negative muon not have that anomaly? Yeah, what about negative muons? It also has a magnetic anomaly, and in theory, it should be identical to that of the positive, right? There's going to be some kind of symmetry here, is my guess. Because of CPT symmetry. Charge parity, CPT symmetry, just say it. Why would you cut it off? CPT symmetry? Help us out here. Charge conjugation, parity transformation, and time reversal, excuse me. Yeah, it's invariant under time reversal. So if you go forward and backward in time, particle interactions are maintained. Parity transform means that if you flip spatial coordinates, it still flips. It works. And charge conjugation means that all particles and antiparticles can be flopped so that you have positive, negative. CPT is a huge demand on the group theory that underpins the particle model. Why is CPT so important? Group theory part of it. Can chat do this? Yeah, CPT is important because it's not just an empirical observation. It's a consequence of how the physical theories are structured. I'm not saying that these theories are correct, by the way. The fact that physicists and mathematicians have been able to draft models mathematically that look like reality is amazing. That's why we're all kind of lit up about it, because there's math that somehow represents what we see. So we get this like chill up our spine that tells us that it's amazing what we've discovered somehow. It's amazing that there's a mathematics, a description, like somehow we're at home, we're at place to understand ourselves here. Weird energy. I know, weird energy, weird vibes. But this is why the tone is so firm from ChatGPT, I think. And group theory plays a central role. Here's a compact but clear explanation. Okay, let's see how it does. Yeah, it's a theorem, not an assumption. We don't know that it's correct. We're not assuming it. And CPT states that any Lorentz invariant local unitary quantum field theory must be invariant under all of those transformations that we named before in CPT. So we're talking about under the transformation of parity, under charge conjugation, and under time reversal. So under these transformations, it has to be that you still maintain the Lorentz metric here. And what is that Lorentz invariant? It means that the laws of physics stay the same for all observers, who are moving at a constant velocity relative to each other. It refers to the difference in observations that are adjusted by relativity. So if two observers are moving at different speeds, for example, or they're oriented differently so that their net motion between each other is not zero, then their observations of a physical process should agree if they take into account the relativistic effect, even if their measurements themselves actually differ. That's right. So anyway, physics should not depend. So the mathematical statement is that something is Lorentz invariant if the equations remain unchanged under the Lorentz transformations, which we named before, the boosts, rotations, or combinations of both. And those transformations together, CPT, the charge parity and time reversal, they form the SO13, or its double cover, SL2C, for spinor fields. If the equations look the same after applying any of the transformations, then the theory is still Lorentz invariant. So the statement of Lorentz invariance is a very powerful mathematical one, and it can only be checked by checking all of those conditions against the mathematical components of the theory. So physicists are heavily locked up, like theoretical physicists are heavily locked up in the process of mathematically inventing models that can work and then trying to test their invariance. Discovering a whole trove of spaces where there's invariance. These are the goals. Holy heavens. Okay, well, that was helpful, but let's just say that the positive muon anomalous magnetic moment, it did get nailed down. Shut down. Can we get a sound effect for that? Shut down. I'll take any fun sound effect that's kind of like, you know, kind of a badass sound. Kind of a badass sound. Like WrestleMania. Showdown. What about Showdown?
Robot Showdown Couple.
These are not good sound effects. Okay, well, I guess we're going to have to workshop that one day. Okay, let's pull back to our bigger list of publications here. What else do we got in Phys Review? That was the muon measurement. When was that? Just keep an eye on the dates. Don't switch pages, please. Okay, that was April 2021. Great job, physics. A binary black hole merger with a total mass of 150 solar masses. Wow. On May 21st, 2019, LIGO and Advanced Virgo observed a short-duration gravitational wave signal with a 3-detector network signal-to-noise ratio of 14.7 and an estimated false alarm rate of 1 in 4,900 years, using a search sensitive to generic transients. So this is like a huge object, is that right? A binary black hole merger with a total mass of 150 suns. if it's from a quasi-circular binary in spiral, these are crazy ways to talk about the geometry of galaxies, or of black holes, that is. I mean, I'm saying galaxies because I assume that like these black holes have attracted a fair bit of attention. Let's take a look at some of the images. The GW event observed in LIGO, Livingston, and Virgo. The top row displays the time domain detector data after whitening by each instrument's noise amplitude spectral density. Wow, it is indeed the same signal by looking at these. The 90% credible intervals from the posterior probability density functions of the waveform time series obtained via Bayesian inference with the binary waveform model, blah, 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 and with the generic wavelet model. Posterior distributions of the progenitor masses, so the two masses that came together to form. Is this just one of them? And this slice taken through here, this shows you what axis. So it was kind of a lump. Really significant density in the middle. God, these are weird images, eh? It's tough to follow this kind of bizarre nonsense. Let's see here. Correction. A. Williamson was missing from the author list of the original publication and has been inserted. Good for you, William. Congratulations on getting credit for what you did. So why is this significant also? Like, and when was it published? This is earlier, right? 2019? 2020? I'm just not sure why. Is 150 solar masses just huge? Okay, it's significant because it broke several rule of thumbs in black hole astrophysics and opened new questions about how massive black holes formed. The black holes were too massive for standard stellar evolution. The two merging black holes were about 85 and 66 solar masses, and according to the existing theory, stars that would produce black holes in the 60 to 120 solar mass range shouldn't collapse directly. They undergo pair instability supernovae, which blow the star apart and leave no remnant. Man, astrophysics really thinks it's onto something, eh? Is that just what's happening? Is astrophysics onto something in a large way? Like what who was it who said that, like, where did the existing theory come from that said that stars would produce black holes in the 60 to 100? That is so specific. Like, obviously someone built a model. They were running the model on a bunch of different tests, and they found that in a very specific mass regime, solar mass regime, they don't get the collapse of those black holes. And that they saw only this very specific exploding apart of two heavy 60 to 120 solar mass objects, which blow the star apart and they leave no remnants. This is just like, obviously, I don't want to be rude. I really don't want to be mean about this, but isn't that obviously not correct? Has anyone watched water swirl around in a tub, or like not just in a 2D plane, but in a 3D plane, or like a 3D volume where there's a vortex forming? You guys know energy moves in really complicated ways. I don't want to be too general about it, but it wisps around. It is strongly influenced by all of the circumstances around it. The energy in the pool. That's what the universe is like. There's a lot of swirling. And if I had to point at the swirliest object in the whole universe, I am pointing at the black hole, right? Black holes are swirly, right? Black holes are swirly. What does that show? And the point is that you expect there to be many possible outcomes, no matter the scale of these black holes, whether they're huge or small. You expect there to be possibilities of all types at all scales, right? I know the particle model of physics might be breaking some expectations because it tells you about the specificity of certain particles existing and their exact energy signatures and their exact properties. You know, we were just talking about measuring the muon charge down to like 9 decimals and finding that anomalous muon charge that we've known about, that we've measured for a long time. Beges, welcome to chat. Not all black holes are swirling. Schwarzschild black holes are not spinning. See, there we go. There's just a whole series of dynamics that could be possible. People think. I don't know that that's true. I would say that the field is not totally certain on it. Let's check in on that point as well. Thank you for bringing that to the chat. Super appreciate the interjections. I'll be pretty honest. I think that it would be weird for there to be a black hole that doesn't swirl, and that's just my gut instinct. That's just me like talking about the universe I grew up in. The short answer is yes. Pretty much all the astrophysical black holes are expected to rotate, but not because swirling is inherent. It's because of how they form. Yeah, that's kind of what I'm saying. It's just like the energy of the universe is moving around. It'd be weird for there to be like a clean cut hole in a very specific part of like the fabric of the universe. That'd be very strange. But general relativity, as you mentioned, allows for a Schwarzschild black hole with Chas mass, but no spin and no electric charge. So a non-spinning black hole is perfectly mathematically valid in the models we have. And yeah, I expect them to be swirly because angular momentum is everywhere. And because these are like the most massive objects in the universe. Like, what are the most massive objects? Objects in the universe. I'm talking about black holes, right? Let's just fact check the crap at ourselves here. Galaxy superclusters. Okay, I'm not adding together all the clusters of galaxies together. They're gravitationally bound. Okay, I'm not including gravitationally bound objects. Is that fair? Also, theoretically, all objects are gravitationally bound. Am I wrong? Is that not? So no stars, no black holes. Whoa, do stars collapse under no gravity? Yeah, I guess so. Like, define. Where's the line between a supercluster and a single star? What's the line between those two things, right? The tricky part is the universe doesn't have hard cutoffs. I mean, that's why this is a tricky part. That's correct. Individual stars have a certain mass and a certain size. So how are we categorizing black holes? I call them objects, but they're not bound by gravity. They exist within gravitational field. Yeah, but are they objects? Are they objects? In the way that superclusters are objects? A supercluster doesn't seem, it seems like multiple objects together. Like, nail this down for me, chat. Superclusters are a collection of galaxy clusters. Gravitational binding is not fully gravitationally bound. Parts of it may be, but the superclusters as a whole tend to expand with the universe. It's considered more of a structure than a single object. Black hole is a single, coherent solution of Einstein's equations. Thank you. It's a single object, right? It's a point mass, technically a singularity surrounded by an event horizon. Yeah, there's something crazy going on, right? Like, I'm not being subtle about this. ChatGPT kind of doesn't get the bigger picture here when it comes to what an object is in the universe. That's interesting. Interesting, chat. Not sure what anything is, I guess. Just talking like everyone talks. A black hole is a true individual object, not a collection of objects. Yeah, I want something. So, what are the most massive singular objects in the universe? That was supposed to be my original question. Let's just fully backpedal. Not collections or patterns like superclusters. Thank you. Supermassive black holes are the most massive singular objects in the universe, period. With 10 to the power 5 to 10 to the power 10 solar masses. Supermassive black holes. There are actual examples. 66 billion solar masses. Oh my God, can you imagine? It just makes me nervous. I get the chills to think about something so large as this. It would envelop the entire superclusters. Like it would just soak up. Well, no, the superclusters are really big. So the black holes are smaller than some. Ooh, that scares me even more. The superclusters are huge. These are single gravitationally bound objects sitting at galaxy centers. And they're currently the most massive confirmed singular objects in the gallery, in the galaxy. So that's what I'm saying. Like black holes, they are literally the biggest objects. Let's see here. We're gonna have to upgrade ChatGPT soon, I think. Yeah, give us a list by mass. That's what we want. Give us a list by mass. Supermassive black hole, supermassive black hole, supermassive black hole. Oh, you're gonna intermediate mass black hole, stellar mass black hole. Then there's a huge neutron star, which is the most massive known neutron star at 2.14 solar masses. Whew, these are scary large, my God. Only singular bound objects are included. Galaxies, clusters, and superclusters are excluded. Mass spans 2 solar masses to 66 billion. It's like such a wild span. Intermediate mass black holes are rare, but some may exist beyond the 150 solar mass merger. We just haven't observed many. So 150 is huge on the scale of these black holes we've discovered. It's enormous. It's not a supermassive black hole like we're getting out in the distance. It's like a big one floating around, a local shark. Scary. We are vulnerable in this universe. And again, that's coming out of Phys Review letters alongside that measurement of the positive muon. Whoa, who's this? Strong quantum computational advantage using a superconducting quantum processor. I am not a robot. I am not a robot. So this is coming out of the Hefei National Laboratory for Physical Sciences at the University of Science and Technology in China. University of Science and Technology in China. Shanghai Research for Quantum Sciences. The Henan Key Laboratory of Quantum Information and Cryptography. And the Shanghai Institute of Technical Physics at the Chinese Academy of Sciences. Here they develop a two-dimensional, programmable, superconducting quantum processor, Suchongjai, which is composed of 66 functional qubits in a tunable coupling architecture. To characterize the performance of the whole system, they perform random quantum circuit sampling for benchmarking, up to a system size of 56 qubits and 20 cycles. The computational cost of the classic simulation of this task is estimated to be 2 to 3 orders of magnitude higher than the previous work on 53 qubits Sycamore. Okay. Computational cost is estimated to be 2 to 3 orders higher. They estimate that the sampling task finished is in about 1.2 hours will take the most powerful supercomputer at least 8 years. Wow. Whoa. So they're doing something that our current most powerful supercomputer takes 8 years to do in 1.2 hours. And I just want to come right back to our conversation earlier today in the stream. Any calculations that we can move from copper and hardware circuits onto light pathways, any calculations, whether it be a matrix calculation or a diagonalization method, or whether it be a novel neural network evaluation, whatever it is, the faster we can make those evaluations, the faster we can bring to life the speed and reality of the ideas around us. We can govern in a large way, instantaneously, the environment around us this way. Right now, it takes our computers a long time. What is that ratio, by the way? Does anyone know that? 8 years versus 1.2 hours. What's the fraction? And now at 1.2 hours, there's one of those every 25 days or so, or one every day or so. So one per day right now. 1.2 hours. Like, it's just going to be such a crazy ratio, right? This is not close. Converting 8 years to hours. Here we go. It's a scale of 100, a scale of the 24, and a scale of the 10. It's 1.7 times 10 to the negative 5 is how much 1.2 hours is of 780 hours, which is how much you get in 8 years. Or in other words, 0.0000171 or 0.00017%. Oh my gosh. Just like, can you imagine having a PC upgrade where it took like, I don't know, 2 seconds to open a browser? And then you're like, yeah, I'd like to get that quantum upgrade. You got any of those sweet quantum chips I could buy? You install the quantum chip into your computer. You open up the same web browser. And instead of taking 2 seconds, it was already open when you thought about it. It was so fast. It was like, you didn't know it wasn't open. There was no recollection of watching it open. It just suddenly was. It's crazy. So this work establishes an unambiguous quantum computational advantage. I think we were all waiting for this paper where we could see the next biggest quantum computer. We want to see the next greatest flex for quantum computing, shut down those classical copper circuits. I think I got to sell all my copper stocks. Copper's going to plummet. Now that we have photonic pathways, copper's going to plummet. For real. For real. Oh, man. This is the last moment to make money on copper, is my guess. How is copper doing? Value of copper. It's around $4.98 a pound. Outlook and forecasts. Yeah, it's going to remain consistent, my guess. I mean, my guess is that it's going to collapse the minute photonics take over the circuit factory. We're not going to be printing circuits anymore. We're going to be printing photo circuits. And if you don't need any copper for circuits, then my supply, the demand dries up, and I'm not going to make any money on copper anymore. Yeah, let's check that historical data if we can. Can we get a chart? Yeah. Over the last, give me 5 years. Oh, it's climbing back up. Yeah. Okay, it's gonna be time for me to be selling that copper real soon. I think we're just gonna have another little bump for a year or two, but don't expect copper to stay around. That's for sure. Okay, so another huge article in Phys Review Letters dropped the dropped the news about the latest greatest quantum computer. Awesome. Okay, topological origin of non-Hermitian skin effects. Oh boy, this is going to be complicated. Let's see here. A unique feature is the skin effect, which is the extreme sensitivity to boundary conditions. I see, as though there's a skin on the surface of a system. Here, they reveal that the skin effect originates from intrinsic, non-Hermitian topology. Such a topological origin not merely explains the universal feature of the known skin effect, but also leads to new types of the skin effects, symmetry-protected skin effects. In particular, they discover the Z2 skin effect produced by time reversal symmetry. On the basis of topological classification, they also discuss possible other skin effects. This could be a dermatology paper, or it could be a physics paper. Here, what I know is that this is going to be fundamentally important because they found a model that works for the quantum mechanical world, is my guess. The skin effect here. What's a non-Hermitian system, just to get us started? Make sure we're on page. It means that there's a non-Hermitian operator inside of the system, usually a Hamiltonian in quantum mechanics, meaning that the operator does not satisfy the Hermitian condition. And in quantum mechanics, we know that the Hermitian operator satisfies H is invariant under the conjugate transposition. Eigenvalues are real. The eigenvectors correspond to distinct eigenvalues that are orthogonal, and observations in standard quantum mechanics are represented by Hermitian operators. This is why a non-Hermitian space makes a good framework for the observations we have. So which non-Hermitian space do we have in quantum mechanics? The Hilbert space. The Hilbert space with non-Hermitian operators. In standard quantum mechanics, states live in the Hilbert space, and normally the Hamiltonian is Hermitian. That is, it's invariant under conjugate transpose. But for open or dissipative systems, you can define a non-Hermitian Hamiltonian, which acts on the usual Hilbert space. I see. So you define an operator on top of the space, which satisfies the non-Hermitian property. Honeys, it's all math here. It's all math all the time. I knew this was going to be a significant paper, specifically because someone's addressing some of the subtle effects that are arising out of quantum mechanics by selecting intrinsic non-Hermitian topologies that produce the skin effects naturally. And they're arguing, like, if you choose these topologies, it doesn't just explain the universal feature of the skin effect, but it also shows you that you should be able to observe other things, other skin effects, specifically symmetry-protected skin effects. And they discovered the skin effect produced by time reversal symmetry. Man, what is that, though? And let's just take this to ChatGPT as well, the whole thing. What is it? The non-Hermitian skin effect is when a macroscopic number of eigenstates accumulate at the boundary of a system. Normally, eigenstates in a lattice are extended, spread throughout the bulk, but here all the states kind of tuck around at the edges. That's very much the real world, I know. Budge says, but doesn't that contradict one of the axioms of quantum mechanics, that all observables are Hermitian operators? I don't think that's contradictory. I think that observables are... Hold on. Oh, man, I don't want to dive into that right yet. I'm going to come back to that in a second. Let me finish learning about the skin effects here. I may have misspoke. Like, yeah, you're getting this from an old rusty can right now. The skin effects are when macroscopic number of eigenstates accumulate at the boundaries of systems. So I kind of understand the energy here where you're getting more solutions to your fields. You're getting accumulation of state at interesting topology. And these are the topologies that you need mathematically to generate those eigenstates. It's Z2. So in topological systems, in topological physics systems, excuse me, they can be classified by topological invariance. Z2 means the system has two distinct topological phases, the trivial phase, I guess they're calling phase, and non-trivial. It's the same kind of classification used for real-time, for time reversal invariant topological insulators in Hermitian systems. Okay, I'm not an expert there. Time reversal symmetry roughly means the system behaves the same if time runs backwards. Okay, we're on page with that. There are two topological classes. The skin modes appear only in the non-trivial class, and their existence is guaranteed by time reversal symmetry. So essentially, it's a new type of non-Hermitian skin effect where topology, Z2 invariant, and symmetry, time reversal symmetry, protect the boundary accumulation of states. That's one way to say it. Yeah, protecting the accumulation. I just call it modeling, but I love that. Yeah, draw the diagram. What is this going to look like? Draw the diagram. Do it. Oh, we have to get plus for that, right? Oh, why did it offer to draw the diagram if it can't do it? That's sad. Okay, let's come back to that previous question around the non-Hermitian system. Hold on. You said, did I use Grok? No, I'm using ChatGPT. Should I use Grok or Gemini instead of ChatGPT, do you think? Is Gemini worse or better? Like they're different. Let me just pull back a second here. Properties of Hermitian operators. Eigenvalues are real. Eigenvectors corresponding to distinct eigenvalues are orthogonal, and observables in standard quantum mechanics are represented by Hermitian operators. And that's a Hermitian operator, and a non-Hermitian system is when you describe a non-Hermitian operator, the Hamiltonian in quantum mechanics. So the Hamiltonian is what describes the space for quantum mechanics by itself, the Hamiltonian being a non-Hermitian operator. All the observables in quantum mechanics are represented by such Hermitian operators. But a non-Hermitian operator, like the Hamiltonian itself, is what defines the space. Again, like I don't have the mathematical rigor to say exactly why that was connected, but that's the mathematical model. You can dive into the math as deep as you want. That is never my goal here, to get lost in the sauce on that. I just want the basics. I want to know what are the arguments and the theories for sure. You're not sure which of the models are best, Grok or Gemini. You heard that Gemini is better at scientific explanations and problem solving, but it was before ChatGPT 5 came out. Yeah, and I'm not even using ChatGPT 5, right? Like I could be upgrading this. We could be upgrading this. Right? I mean, maybe I should be upgrading Gemini. We could spend some time asking about who's the better model. And I don't mind cross-checking. Again, red flags for me. Any of this could be wrong information. So just take it all with a grain of salt, everybody. You cannot guarantee one way or the other that these are the absolute truths. I don't mind cross-checking things too. If you guys want, just say so in chat. I'm here for it. But mostly I'm trying to get a sense of what's being published. The fact that these are the top articles in Phys review letters, that's what sets the stage for our interest, right? And it's the interest that we have in topological origins of non-Hermitian skin effects has to do with that publication's position on this Phys review letters list. It's a total hack for us to be looking at the top publications, because I don't need to be an expert to know that a lot of experts care deeply about the outcome of this article and about the skin effects, the non-Hermitian skin effects that you see in quantum mechanics. I know people care. Now, a lot of people care as well, right? We're talking about 1,200 citations here. Does it show a number of citations here? No, it doesn't. No, it just, oh yes, it does. 1,000 citations. There you go. This publication has been cited 1,030 times. 43% of its citations were received in the past 2 years, which is higher than you might expect, suggesting that it's currently receiving a lot of interest. It's a big deal. It continues to be a big deal. Dude, this is handy. Dimensions? I love this. Compared to other publications in the same field, this publication is extremely highly cited. It has 276 times more citations than the average. So the average publication has 1 citation. It's not a very helpful metric to say that it's 276 times higher than 1. Jesus. And so what did we look at in total in Phys review letters? We saw top of the charts. Positive mu on magnetic moment measurement. Check. It wasn't 2 like it should have been for a spin 1/2 particle, for a pure spin 1/2 particle. It doesn't act like a point particle. It has subtle effects, anomalous effects, and they were measured. Number 2, hugest black hole. I mean, it's not the hugest. It's not a supermassive black hole, but it's the biggest merger that we've seen. We expected the merger not to occur. Should have been that black holes of that size should have exploded and blown away from each other, but we observed the merger of 2 huge black holes. So there's a whole question thrown up in astrophysics. What's wrong with your models? Why are those models wrong? Article number 3, where a Chinese group pulls out the latest, greatest quantum computer, strong quantum computational advantage, where they show that in 1.2 hours, you could do what takes on our fastest supercomputer 8 years at the moment, which from my memory is, yeah, it's 0.00000717 of the original time. So quantum computing is going to swallow chip manufacturing in the coming years. That's number 1, 2, 3, number 3 in the last 5 years of top articles and Phys review letters. Man, it's hot in Phys Rev, dude. It's hot. And then the topological origin of non-Hermitian skin effects, which is a modeling for quantum mechanics for which the entire physics community has been so thirsty for so long. So you're getting 1,100 citations there, and that is coming from the very thirsty community from which it was based. Okay, and after that, you're going down to the sub 1,000 citations. These are not subtle papers. It would be important to come back to these papers and to look at these. I just didn't want to get too lost in the sauce on physics, but gotta do what you gotta do. What's this? Improved constraints on primordial gravitational waves using Planck, WMAP, and bicep Keck observations through the 2018 observing season. Okay, so this is a seminal paper for the working groups who are narrowing down the parameters on gravitational waves. Primordial gravitational waves? Can someone just get me the Cliff's Notes on that? Gravitational waves? Compared to what? I swear to God, if we run out of chat funds, I will actually pay for chat. If it starts refusing to answer questions, I will throw money at this. The primordial gravitational waves are the ripples in space-time generated by the very early universe. I see. So primordial in the sense of the primordial universe, which implicitly for humans refers to Big Bang. So they're saying this is like a primordial moment. I have a hard time with those descriptions, calling something the start of something. I've never seen time start or stop, so I don't have a sense that there necessarily was a start or a stop to those moments. But if they wanted, yeah, maybe I'm stepping too far here. We're not talking about the time starting or stopping. We're talking about the universe matter itself. Noted. All right, so they improved the constraints on those primordial gravitational waves using specific observations through Keck, BICEP, WMAP, and Planck. So maybe they achieved a much better measurement because of the number of measurements who came together. It's a huge collaboration, by the way, and physics coming out of Cambridge, Illinois, Minnesota, University of Cincinnati, it's California Institute of Technology, it's Harvard and Smithsonian, it's the University of British Columbia, it's SLAC, it's French laboratories in Grenoble. It's a huge international working group. Let's see, they present the results from an analysis of all the data taken by the BICEP-2 Keck array and BICEP-3 CMB polarization experiments, cosmic microwave background polarization experiments, up to and including the 2018 observing season. This just seems like a little late. When did this come out? Like, aren't we waiting on this kind of? Published 2021? Man, this took a long time to compile. We add the additional Keck array observations at 220 gigahertz and the BICEP-3 observations at 95 gigahertz. And the QU map now reach depths of 2.8, 2.8, and 8.8 micro K Coulomb microwave background units. I do not know what these measurements are. What is happening? They have an improved signal to noise ratio on polarized dust emission. They take auto and cross spectra between the maps and publicly available WMAP and Planck maps, and they evaluate the joint likelihood of the spectra. So this is a very mathematical approach to building the data into something more complex. We appreciate this. The foreground model has 7 parameters, no longer requires a prior on the frequency spectral index of the dust emission taken from the measurements on other regions of the sky. Dudes, I do not know enough, but the point is that running a maximum likelihood search on these simulations with unbiased results found what I'm assuming is the strongest sigma value they've got yet. These are the strongest constraints to date on primordial gravitational waves. Yeah, I mean, I would never know that this was significant. I would never know that this was significant. I would never know that this is significant. And if someone tells me they have the best measurement, I know it must be important to them. It must be important to that community. And that's not subtle at all. That's article number 1, 2, 3, 4, 5. Top 5 article, most cited. Phys review letters. Like, those folks, they're getting funding. Great job, Ahmed. Great job. Who else do we have here? The measurement of the permanent electric dipole moment of the neutron. Holy crap. Holy crap. When? Published February 2020. We present the result of the experiment to measure the electric dipole moment of the neutron. Now, why is that so challenging? Why is it so hard? Uh-oh, I hit the free plan limit for ChatGPT 5. Ooh, we got to pay for this. We got to start paying for this. Okay, I will pay for this. I will before our next visit. I will. Why is it so hard to measure? I don't think this is going to significantly bias the outcome of this answer, by the way. Why is it so hard to measure the electric dipole moment of the neutron? Like, I'm just going to pitch my guess. It's hard to measure it because you can't control neutrons. Neutrons don't have a charge, so you can't use a magnetic field and a bunch of magnets to position the neutrons. So when you do neutron experiments, you're just begging for some kind of neutron source that is coherent, that is consistent. But let me just see. What is it? Oh, no, I was wrong. Straight up, look at this. The neutron has an extremely tiny magnetic dipole moment. And maybe we expected it to be 0. Maybe we expected that dipole moment to be 0. Why isn't it 0? And the short answer is the standard model predicts it to not be zero. It is based on the fact that it is massive, right? Just to clarify, why isn't it zero? An electric dipole moment violates both parity and time reversal symmetry. Ooh, so if the neutron has a non-zero EDM, it signals CP violation. There it is. You don't get Lorentz invariance if the neutron doesn't have some kind of moment. There it is. And they expect something very tiny. Since the neutron has no net charge, the effect is only observable via the torque that the neutron itself experiences in an external electric field. So unironically, you have, let's just get paint out here. Man, unironically, you have these particles that you can't even control a neutron. Gray is the right color for a neutron, right? You have a neutron, and that neutron has a tiny magnetic dipole moment, just like, I'm going to draw it way too big just to show, but it's like, it has a net positive over here, it's net positive over here, and has a little bit of a net negative over here. So the dipole itself, this arrow that I'm drawing, this dipole moment, it's kind of like there. But the only way to measure that is inside of an external electric field, which let's just zoom this out, right? Which if it's such a tiny little thing and our electric fields are huge, like I know we have very large electric fields, but you have to generate a very small one for this experiment, then you're waiting for those fields to be interrupted and you're waiting to observe what it is that happens to this tiny little particle, this neutral. It's not even charged particle. Whereas for charged particles, you can strategically manipulate the motion of the particle, give a stronger signal, or generate another type of radiation that would allow you to observe it. There's so many ways. I could go through the Leo list of theoretical particle physics approaches, and you can get a massive laundry list of all of the techniques for detecting various particles. Maybe we'll crack open my copy of Leo and see what's there for neutrons. I had a friend who was doing neutron experiments in Lund, Sweden, and their key was that they relied on random neutron emission in order to conduct the experiment. So it took them a long time to gather data, or it took them a long time to figure out how to use that data. Really, they had to create neutron detection somehow on the other side in order to make up for the random trajectory of the neutron. But that's hugely problematic because I shouldn't say there's no. Detecting neutrons, again, because they have no charge, is extremely challenging. So how do we detect the neutron moment? The neutron's moment. So the neutron also has a spin, yes, of course, and a magnetic dipole moment. If the neutron also has a little electronic dipole moment in an electric field, it experiences a torque. And then it adds a tiny additional precession to the neutron's spin. So how do we measure the spin? And then the spin precession measurements. The core experimental technique uses Ramsey's method of separated oscillating fields. Guys, what is going on? You polarize a bunch of the neutrons so that all spins point in the same direction. Then you put them into the magnetic field that's uniform, and then the spins precess around that magnetic field the way they would naturally. So you start by just polarizing a bunch, and then you measure the frequency of all the neutrons. So any of the neutrons that were modified or that were changed would show a distribution in that measurement of the frequencies. Of the Lamour frequency, it's known as. So, man, this is nuclear magnetic resonance imaging. This is an MRI. This is absolutely MRI for anyone who's wondering. MRI uses two techniques, though, uses the same technique, but along two different resonances. Not just the Lamour resonance. There's a second frequency, not just they're called T1 and T2, not just one resonance, but also the second one. But any resonances that exist, magnetic resonances, you can measure. And then you measure that tiny frequency difference when you switch E when you switch the electric field direction. And that difference should be proportional to the electric dipole moment. So, and apparently we're using ultra cold neutrons. Dude, this is so much work. Physics completely jumps the shark on itself over and over again. It's absolutely the most complicated space to be in, and it's absolutely the most wonderful. They're slowing down neutrons to ultra cold speeds, 5 meters a second. Neutrons that move at 5 meters a second. So that can be stored in neutron traps for hundreds of seconds. And there it is. When did these neutron traps show up? My friend would have killed for that technology 20 years ago. Wow, so much work. When did we develop neutron traps? I mean, good ones, not the old ones. Yeah, the concept of neutron storage has been around for a while. I'm on page with that. As I mentioned, my friend was naming neutron trap as a tool before it existed. Typical cold neutrons still move too fast to be reflected by materials and walls. In 1968, Fermi and co-workers proposed that very slow neutrons with energies below 300 nanoelectron volts could be totally reflected from certain materials. Amazing. They move so slowly that they can be trapped in material bottles or magnetic gravitation traps, like literally bottling up the neutrons. Phenomenal. Phenomenal. The first experimental neutron storage in a material bottle was literally in 1969 by researchers at the Soviet Union. And those neutrons lasted several tens of seconds, way longer than the flight times in normal beams. Since the 1980s, ultra-cold neutrons have been widely used to trap materials with very low neutron absorption, for magnetic and electric field uniformity, and for cryogenic techniques to reduce neutron loss. So, summary, 1960s conceptually, Russia comes out in 1970 to pull it off, and then modern high-precision experiments in 1980 and beyond. Dang, dude. So are they expensive? He just didn't have good ones? He couldn't supercool the neutrons? Yeah, they're super expensive. Oh my gosh, you need a nuclear reactor. Like the Lau Langevin in France. He was working in Lund. Lund, Sweden. Yes, there's a significant neutron science infrastructure in Lund, mostly centered around the European spallation source, the ESS. Once it's completed, the ESS will be one of the most powerful spallation neutron sources in the world. The Highness Project. The Highness Project. Let's go. Get highs. Get highness. To build a second neutron source at ESS, right below the spallation target. Well, what was already there? The neutron irradiation facility? They have a huge source testing facility for neutron irradiation. So they have these nuclear sources. That's why he was working in Lund. They also have a compact accelerator-driven neutron source, CANS, in their applied nuclear physics lab. Oh, wow. Yes, very much so. Oh, wow. So in this publication, they nailed down the permanent electric dipole moment of the neutron. We did it, finally. 2020. And is it just a better measurement than before? How good is it? Times 10 to the negative 26. That's how good the precision is. Did you see this? How insane that precision is? The dipole moment of the neutron is approximately zero-ish, plus or minus 1.1 for statistical error, plus or minus 0.2, or sorry, 0.2 for statistical error, 1.1 for, 0.2 for systematic error, times 10 to the negative 26. Times 10 to the negative 26. The dipole of the neutron is known. I tell you, it is known, practically speaking. Jesus. And that's paper number 1, 2, 3, 4, 5, 6. That is the 6th most cited article out of Phys Review letters over the last 5 years, following on the tails of 2,000 citations, 1,400, 1,100. It's 1,000. It's 950 here at the measurement of the permanent electric dipole of the neutron. Dude, it has been a magnificent last 10 years in physics. It's been like, I don't think we're going to stop here. We're going to keep going down this list. Like, I'm bold enough. I'm bold enough to crack into these quantum mechanics papers where we talk about the advancements in our non-Hermitian or Hermitian operating spaces. Like, I'm willing to do it. And I think if we read enough of this, maybe even we'll understand. One day. Maybe no physicists even do. Oh, Christ. I just got to say, that was an outstanding literature review today. I was so pumped to see some Phys Review letters. I have a hard time linking into other spaces, into other journals. But man, Phys Review, that is my baby. That is my one. That is my bae. Thank you for joining me today on our review, our lit reviews days. Please come back next Tuesday when I do this again. Actually, I'm not going to be here next Tuesday. I'm not going to be here next Tuesday at all. I'm going to be on a little trip. See you later, Bajas. Thank you so much for coming in here. Super appreciated having you in the chat. The thoughtful questions here on the operator. I really appreciate that challenge. It's good to keep our facts straight. I don't understand it. I don't understand it. I've solved some mathematical systems in non-Hermitian space because I've done graduate quantum mechanics, so I've had my moments, but it's not like I intuitively feel it. I'm not at the level where I know what's needed all the time, right? I'm at the level where I cross-check all the requirements. I check to see what symmetries need to be maintained. I check which violations could occur, and then I'm really systematic about it at this point. So appreciate everybody who came in here and struggled with me. Come out for not next Tuesday, but the Tuesday after that, where I pick up another literature review day. Come out tomorrow for my Wednesday Buildness Day. Again, I'm going to be out there. I'm going to be building software to help run this stream. Dude, thank you so much for the follow. Much appreciated, Budges. Much appreciated. Welcome to the silliness crew here. Sorry, my Twitch alert sound didn't work there. I realize it. I'll fix that. I'll be back on tomorrow morning at 9 o'clock, same time. Okay, same time. I know I was an hour and a half late. I'm trying to figure this out. I'll try to be here on time. 9 o'clock. 9 o'clock Pacific time. I heard we're going to stop doing our daylight savings time here. That might be the case in British Columbia. Or maybe even in Canada as a whole. That'd be sweet. Would love that. Friday, I'll be building factories, and I know I've been playing Satisfactory religiously in my private time, but I promise I'll come here and play Factorio on Friday, this Friday. It's my gift to everyone. I'm actually kind of dying to reopen that factory. It's been a while. So come back for that. I'll be here again on tomorrow morning, as I mentioned, on Friday, but next week I will be away on the Tuesday and the Wednesday. I'll be back for the Friday for the factory again next week, though. And who knows, maybe I'll offer a little random weekend stream at some time in an afternoon or evening this weekend. But otherwise, thanks so much, everyone, for joining me on this literature review. I gotta say, it's pretty exciting to see what's going on there. I might be struggling, but the literature sure isn't. Those working groups are more efficacious and more packed with grad student knowledge and effort than ever before. I can see that. So regardless of what you're doing, make sure you keep on struggling at whatever level that looks like for you. And join me next time.